was very, so I mean this was a robot that has the capability actually to go over a rough terrain. This is not an indoor kind of a machine. It has a suspension, the wake, the steering capability to maneuver all this, and we actually tested it in some parts. Now, again, a very important consideration for us was that, well, if this is sort of the cartoon of the robot, then you have to put in the metal detector or the ground penetrating radar or whatever that has to detect the mines underneath. You have to put it very close to the ground, okay? And in a real terrain, the ground profile, it changes. Okay? And not only the ground profile changes, but sometimes it encounters sort of rocks or obstacles, which it has to sort of bypass or something. So you have to design an arm here, which here it is sort of a cartoon, not the actual arm, that needs to move this sort of thing up and down maybe, and even sideways to do this sort of a terrain traversal. And also this is sort of a 1D view. You actually have to do this for the entire terrain, because the rule book said that as the robot is moving, you have to sweep an area of a certain width, I think 1 meter, maybe. What was it? 1 meter around? 1 meter around its center, and so as the robot moves along, the 1 meter around it must be cleared. So what we came up with as our design, again, in keeping, I mean, the thing in our mind was simplicity. To keep the thing as simple as possible was sort of this forward movement, that you can have some kind of an arm which sort of moves up and down. I'll just shortly explain to you what that is. So some sort of a raster scan like sweep. So the forward movement, it produces the forward sweep, and then in this direction there should be some sweep that should do. Now this sort of the sweep on this axis can be done either two ways. Either you put a redundant, maybe multiple sensors here to do the sweeping, or you put a prismatic joint here. So I mean, in the current sort of incarnation of the robot, this joint is still missing, which we hope to incorporate very soon after the robot arrives. Again, I mean, this is a sort of a very simple and straightforward concept. This was the mechanical design that we ended up with. This is a 4 degree of freedom actually link. So there is actually a joint here. This is a prismatic joint, sliding up and joint movement. There were 2 joints here. And again, this was the prismatic joint I was talking about. There should be a movement in this direction, which has still not been incorporated. So again, this Adnan actually did the mechanical design. The manufactured arm has been is shown on the top right corner. Power electronics again was very interesting. That we actually made the power electronics in such a way that once you do this, then you can port it into multiple platforms. So for example, the Duldul robot and the Marwa robot, they have very similar power electronics, and we actually had to put in slave microcontrollers for each of the actuations independently, because we wanted to have some kind of a teleoperation capability as well. Simple radio receiver, so that if everything breaks down, you can at least have some way of bringing the robot down back by manual action. Now, so this was the regular design. The software backbone was something which actually just helped us a lot. And this is due to ROS, the robot operating system that has sort of taken the robotics community by storm in the last 2 or 3 years. And the basic philosophy is that, so this was initially started by Stanford. Then Willow Garage is actually an outfit in Silicon Valley. It is now distributing this ROS, but again with an open source Linux-like development strategy, that you can just go install it on your machine, on like the machines that we use, and then not only that it is just like an operating system or whatever, actually sitting on Ubuntu, or there are other operating systems that it supports, but right now we use Ubuntu. It provides hardware abstractions. It gives you very good a range of drivers and controllers for, say, for example, you want to put in a laser scanner, then the driver is already there. You can actually use it. If you want to have multiple processes, like the jungle of processes that I showed you, if you want to do message passing, sharing variables, data logging, visualization, those kind of things, so already all the support is there. And there are packages. So people, what they are doing now is that they are building these. For example, you write a paper on a new technique. They test this thing in standard C++ like algorithm. They package it into the form of a ROS package, as they call it, and they make it freely available for others to use. So that was something that we used very intensively, because I mean, like we said, we didn't have the bandwidth to do everything ourselves. I mean, those are full research problems by themselves. We simply cannot do all of that. But this sort of pick and reuse type of strategy worked very well for us. So for example, the ROS computational graph, as they call it, I mean, you can actually map it to this. These are bags where the data logging takes place. All of these processes, you call them as ROS nodes. These lines you can think of as topics, as something being shared, and so on. And then this top level controller is actually the ROS master. So I mean, the mapping was actually very, very natural, sort of. And I mean, this happens in all robotic systems, I'm sure. We had to use some external libraries, like for example, OpenCV for computer vision-like tasks, PCL for point cloud manipulation to be used in, for example, SLAM, RGBD SLAM, GL viewer for visualization again to saw point cloud and so on and so forth. So I'll just again, we are out of time, right? We are almost out of time. I'll very quickly show you two critical tasks that I think those were the tasks that blew the judges away. I mean, the rest was interesting as well. So one of the things that we did was that we built a stereo vision systems ourselves. Again, it's not as if that we built it from scratch, but just to demonstrate that you need not buy a complicated, very maybe like $2,000 system or $3,000 system off the shelf. You can just take regular webcams, put it on a piece of wood for calibrate it. You at the back end use simple PCL OpenCV computer vision library. Do a little bit of a tweaking, calibration, and then you can actually have very good stereo vision. So initially we were concerned that, well, the cost would be very high. Maybe we need to use a laser. And how would you actually calibrate such an equipment? But thanks to the hard work done by our engineers, and especially Talha, who actually worked on this part, we actually did this. And the cost was sort of minimal, just two webcams put on a stick. And you can, as you can see here, this is actually mounted here and worked very, very well, actually. And this was actually something that sort of did the arm movement. So we had to did some calibrations. There is some sort of image rectification that needs to be done here. You can see Talha doing the calibration part. This is a dance he does in front of the cameras when you have to move it for the first time. So every time the robot is shipped or something, the calibration it gets disturbed, but then he has to do it this way. So these are some examples of computations. Again, there's a pile of sand somewhere in LUMS. He takes the image. This is one of the images, maybe the left or right hand side, compute the disparity map, and worked out very well. Okay. This is again another one, for example, the speed bump coming in front of the robot. This is an actual trial. So two pictures, and then you can actually fit in the plane of the coming. So the basic tasks were image acquisition, the rectification, the calibration part, block matching between the two parts, point cloud generation, and then the plane fitting of where the ground profile is. So why we use some very simple PCA kind of a thing. Again, so some of these things are simple, some of these things are not. It's an integration of many parts. So the visual servoing part is just shown here independently in Talha's desk here. So it has this arm, the vision system looking down, for example. And these were the controllers, and so the entire thing, this is the PC on the side, which is sort of doing closing the loop in some sense. Some LabVIEW code on the top showing what is going inside this SBRIO card. And then this is, again, we play it very quickly just to show you, for example, he training the actuator, for example. So it sees the obstacle and then it will try to adjust itself to the obstacle. So it's a long video. I'll skip it. So there's more coming actually by Talha very soon. The second very interesting part was the visual odometry and the SLAM part. Okay, and for that, again, we needed that because we needed to have very good map accuracy, area profiling for mine localization. I mean, the GPS map is not gives you the detail to actually tells you where the mine actually is. So either you can do it physically, maybe put some kind of a chalking mechanism, you drop the chalk where you detect the mine, or you can actually, if you want to do this electronically, you have to build some very exact maps. And also for navigation and autonomy, you have to build these maps in order to navigate through the obstacles and so on. So very hard problem. What we did was that, we said, well, this is a common portable, that we should develop it once and then sort of calibrate it to different robots. As you saw that there were multiple robots that we used, and we had to do it within our means. So what we did was that we use open source again development platforms such as ROS. We took some standard code, which was provided by some people but tweaked it. Then the low-level control was performed by NI, so there was some sort of an integration there. And then, most critically, the vision sensors, we could not afford to buy laser scanners, but we just took this Xbox gaming device, Kinect, and we used it for that. Now, this, I think, for the participants who do not know about it, I think this is a wonderful sensor to have in order to kickstart projects. For 12,000 rupees or $200, you can buy this thing, which essentially gives you the same performance. Well, I mean, I should be careful here, but very similar performance to, say, a 10,000 euro sensor, which is like a laser scanner or something. So, I mean, this can at least get you started on doing, maybe in the indoor environment, some real things. So, it is basically an infrared depth plus regular camera. I mean, there's a lot of deep science behind how they came up with this. Now, what we did in our project was one problem for us was, well, how do you actually represent, for example, maps? Okay. So we used, again, we just looked up the ROS in which the different packages available and the research that came out. For example, one group at the University of Freiburg, they gave this Octomap representation for outdoor environment. So this is, so you get the point cloud, and then using this this framework, you can actually represent it at multiple resolutions. So this is our lab, the lab upstairs where most of our RAs are. And maybe if you can see some small arrows, this is the movement of the robot inside the lab. This is the telepresence machine. And this is, for example, the Octomap that is built from this thing. So once you have a map like this, then, I mean, again, tasks like navigation is not that easy, but now you begin to get handle on what you can do. And also, for example, for SLAM, we also picked something which was RGBD SLAM. This is one indoor map generated by a robot. There are multiple steps. There's no time to explain these steps, but again, if we had to do all of this ourselves, because the paper is available, it's published, if we had to replicate it ourselves, it's maybe 1 or 2 man years time to replicate it just. But because the thing was available, we sort of ported it, tweaked it to a large extent, and then sort of used it. And so these are some trials, for example, outside our SSC building, one of the early ones where you are moving this robot around. I think we can see Ramiz here, maybe sitting somewhere. One of the things which it is picking. And so the robot sort of moves around, it picks up things, and then it sort of builds a map of the environment. So this is a typical SLAM. And one of the typicalities that you would see here is that, for example, you initially build a map, and then you're trying to close a loop, and you see the defect. For example, this bush's line is here, and then this bush line is here, because as you're moving, there is problem with your odometry. And when you close the loop, then that sort of thing that gets removed. So maybe down here, it's perfectly stitched together. So and this shows you very typical sort of SLAM-like behavior, and this is now outdoor, all done on outdoor. I'll show you I'm out of time. Integrated test, the speed bumper test, as we called it. So now let's test the 2 systems together. In fact, all of the systems. There is a bump. Can the robot go over the bump, adjust the arm as it goes along, build the map while it does that, does some kind of an autonomy, sort of a path planning kind of a thing. So we did that, and then this is one. Again, the details of this is actually coming up in the coming talks. So I'll just show you some snaps. This is the result of the arm movement is actually coming later on. These are results of the SLAM. So the point clouds, they clearly show the maps being built. If you notice the small line in here, this is actually the robot path that the algorithm has actually calculated. So the map itself and the position of the Kinect sensor, which is actually the robot moving along. So at the same time, I mean, this problem is like a chicken and egg problem. You are trying to explore the map, but you're also trying to localize yourself with respect to the map. So that's a hard problem, but now mostly solved in the last maybe decade or so. But we demonstrated that yes, we can actually do this thing. So in multiple shots and also the arm movement, the same test, the arm we see whether the sensor is moving, and as you can see from the normals, it is actually sort of doing the tracking of the bump. So I would have shown you the video if there was time, that the arm is sort of tracking the bump. So we did these kind of tracks, and then there was some snapshots from the field trials. We still do not have access to the media, the footage from the actual trials, because it happened inside a military base. We were not allowed to photograph there. So more will be released as we move along. And of course, there is a paper to write, so we should not I shouldn't release everything now. Okay, so very quickly, lessons and conclusions, and this is, I think, the main part. I think the achievements was that we demonstrated basic functionality. Okay, and this is what we wanted to do. We just wanted to show, well, we can build a real robot, we can make it move around. Yes, it's not as great as some of the things that you have or other groups, but yeah, I mean, there's something that we can do. Mechanical design is sound, but actually needs another look. So we will do another cycle. Again, thanks to this Alvida project. That's exactly the one agenda item, to do the design one more time and to do this more. Surprises was that I actually did not expect this, that we would be able to demonstrate this sort of mapping navigation performance on real terrains. And the visual surveying performance also using these stereo cameras came to me as a bit of a surprise. Not that I doubted that it can't be done, but with the capability that we have and with the time we had, I had actually big question marks in my mind whether we should go via this route as well. But when we looked at other teams who actually did not go via this route, they brought in arms which were equipped with ultrasonic sensors and doing ground profiling with that, nothing worked with, for them. So it was clear that this was the way to go, and this was probably what sort of set us apart. Now the limitations was that one of the things that all of the experiments that I've shown you, they were all conducted after 5 p.m. If people who noticed us outside in dengue time, every day, this was because the sensor does not work in direct sunlight, because it's not for outdoor applications. But because this was the only sort of instrument that we can afford, so that's why we sort of said, well, okay, let's take the $200 sensor, but now let's take it outside. The 45 minutes we have till sunset, let's take it out on ride and see what it does. So, of course, this does not work in direct sunlight. We need to get better sensors. And then again, of course, thanks to this project, now we are getting some laser scanners and so on and so forth. Visual detection of mines, that was part of the project, that if there is a mine just lying outside, you have to detect it. That part actually we could not incorporate. This was actually the reason that they gave us the smart cameras. We desperately, at the very last minute, because there was so much going on, we gave one of our student groups this task to, okay, just maybe throw out a Coke can and try to detect it, and they came up with some results on that. But they were not sufficient to actually just prove that we can visually detect mines. But this is a very separate, I think, expertise from what we have. So any image processing expert gives us the right algorithm, we port it to the smart camera, and then, but in the robotics part is exactly clear. And then user interface was very, very basic and very lab-like. I mean, like, this is, we need to work here. I think so. I mean, we know and you know what is going on, but nobody who's staring at our code actually knows. So we need to have a decent user interface. So that's maybe something which is missing at the moment. Acknowledgements very, very quickly. I just again want to thank National Instruments, the Arabia Division, the Faculty Initiative Fund, which made it possible. Department of Electrical Engineering at LUMS, we actually ran out of funds at the end by about maybe 100,000 or something. But that was pulled together by multiple sources, in one of which was the department. And then I want to give full credit to Hamza Engineering, who actually built the robot. Okay, so this sort of, we are very lucky that in a country like Pakistan, we do have capable people who are building scientific instruments. So this guy is actually doing marvels, no formal training, but doing stuff. And then Orgosoft was another outfit that actually they partnered with us, and they helped us develop a few things. Okay. So with this, I come to the end of my talk, and again, took more than what I wanted, but nevertheless.